Welcome to BookmarksEducare. Today we will be starting with the lesson. Previously we have already seen, we have talked about metallurgy. We have seen the occurrence of metals. The introduction part was covered. We will now begin with the main part, that is the metallurgy part, where comes the extraction of the different metals from its ores. So directly moving on to that part is what is metallurgy, right? So metallurgy is the process of extraction of pure metals from their ores. So as we have earlier seen that ores are nothing but minerals, and minerals generally are the metal associated with some earthly impurities that are known as gangue or matrix. So when you extract that pure metal from the ore, then that process, there should be some process. That process is nothing but known as metallurgy. So it is the production of pure metal from ores and also the manufacture of alloys. So in any production, what happens? There should be different steps in the production. So in order to extract a metal from its ores, there are certain steps. So the first step is, as you can see here, it is you take the ore, you have to first crushing and grinding. So the ore is a macroscopic or a big particle. So in order to extract the pure metal, first step comes what? You have to crush or grind the ore into finely divided particles, right? So this crushing and grinding is generally done in ball mills or jaw crushers. Here you can see a picture of a ball mill and jaw crushers. So you just insert the ore into the ball mills. It will crush it to finely divided particles, and the process is known as pulverization. The crushing and grinding of the ore is known as pulverization. So the first step is crushing and grinding. Next is concentration. Concentration means ore dressing. So how do you do this ore dressing? It is like you have different steps in doing the ore dressing. The first methods are, the first is gravity separation, magnetic separation, froth flotation, and chemical method or leaching. So there are 4 different processes in ore dressing, which is gravity separation, magnetic separation, froth flotation, and chemical method or leaching. After ore dressing, what happens? You have to process that ore into its respective oxides. That means that is done by 2 different methods. One is roasting, the other is calcination. Okay? After you have converted the ore into its oxide, and why oxide? Because from the oxide it is very easy to reduce the oxides to form metals. That is why any type of ore is first converted to its respective oxides. So that oxidation process is done either by roasting or calcination. Next comes, after oxidation, what? You have to reduce the oxides to its respective metals. So the next step is reduction. Reduction, 2 types you can do. One is by chemical method, where you use certain chemical agents like carbon, hydrogen, carbon monoxide, and it can also be electrolytic reduction. Okay? After that comes refining. Once you have obtained the reduced metal, still it contains some impurities in it. So the purification is done by the refining method. Refining can again be done by different methods like distillation, liquefaction, and also electro-refining. So after refining, what you get is the pure metal. So these are the following steps by which you can extract the metal from its ores. Now we will go into the detailed process of each and every step. So the first step, as I have discussed, we take the ore, we will give it into ball mills or big jaw crushers. It will crush and grind the ore to finely divided particles. That process is known as pulverization. Step 1 taken care of. Now step 2 is the dressing or concentration of the ore. So dressing or concentration means what? I said that ore is metal and it has certain earthly impurities, that is the gangue. So you have to separate the ore from these impurities. So this process of removing the gangue or rocky materials like silica from an ore is known as ore concentration or ore dressing. Ore concentration or ore dressing. And the purified ore is known as concentrated ore. So, from the ore, when you remove the rocky impurities or the earthly impurities like gangue, you get what? You get the concentrated or pure ore. This can be done by the following processes. One is gravity separation or hydraulic washing, magnetic separation, froth flotation, and the chemical or leaching method. Now, coming to the first process, that is gravity separation, hydraulic washing or levitation. What is the process? The principle that is used in this method of ore dressing is the difference in densities of the ore particle and the gangue material. Therefore, it follows, as because there is a difference in density between the ore and the gangue particles, you use this gravity separation. What is the method? If you see in the picture, you have a corrugated vibrating table, right? And you have a flush of water, okay? So this finely divided ore particles are dropped on this vibrating corrugated table which has grooves in it. You see, these are the grooves. And you have a flush of water. Now what happens? The ore particles are denser, so that is why they settle down at the bottom. You see the red particles? These red particles are the ore particles which, being denser, settle at the bottom and are collected in the grooves. Whereas the gangue or impurities which are lighter, they are flushed down by the water. Okay? So you see that as because there are density difference between the ore particle and the impurities, this is how you can utilize the gravity separation technique to separate the ore particles from the impurities. Next is magnetic separation. As the term magnetic separation comes in, that means the principle is that magnetic ores or magnetic impurities can be separated using this method. How? You see that in the figure there is a conveyor belt. You flush the ore with the impurity through the conveyor belt which is rotating on two wheels. One wheel is non-magnetic and the other wheel is magnetic. Okay? So if as impurity I have a magnetic impurity, say suppose in tin stone, which is an ore of tin, SnO2, it has magnetic iron oxide as impurity. So you have to separate iron oxide from SnO2 in order to generate the ore that is free from the impurity. So if you pass tin stone and the impurity through this conveyor belt, what will happen? Fe2O3 being magnetic will be attracted towards the magnetic wheel and the non-magnetic particles will drift away from the magnetic wheel. So this is how, utilizing the magnetism property, you can separate the magnetic impurities from the non-magnetic particles, right? So this is how magnetic separation can be used for concentration of ore. Next comes froth flotation. Froth flotation, the principle involved is the preferential wettability of the ore with oil. Oil means here pine oil, that and the gangue particles by water. So This depends on the wettability property. That means the pine oil wets the ore material and water wets the gangue material. How happens? You see the image. Here you have a tank, right? In this tank, you have what? As a solution, you have pine oil and water. Now you have the ore particles also inside this tank. Compressed air is passed into the tank and also potassium ethyl xanthate is added. This tank is then agitated. What happens? The pine oil, they wet the gangue ore particles, and the ore particles being lighter, they drift towards the top of the tank at the surface in the form of froth, and the gangue particle being denser, they are wetted by the water and they settle down at the bottom of the tank. So you see the concentrated ore particles therefore comes in the top in the formation of froth, and the bottom is the gangue material which is settling down at the bottom of the tank. So this is how pine oil and water, mixture of them, and on the principle of preferential wettability, you can separate the ore particle from the gangue particle. Next is chemical method or leaching. In chemical method or leaching, what happens? You take a additional chemical reagent, say a acid or a base. Now that reagent will react with the ore particle, that will solubilize the ore, and the impurities or the gangue particles will be precipitated, right? So this is how you can separate the gangue particles from the ore particles. Next, to the solution or the filtrate, you add another agent that will precipitate the ore. Then what happens? You get the pure ore from the separated from the gangue material. So this is the concept of chemical method or leaching method. Now, this is usually done for concentration of metal ores like silver, gold and aluminium. So after concentration, what happens? After concentration, what happens? Even the ore contains still certain impurities as gangue, which is again then mixed with certain additional reagents which are known as fluxes to form what? To form a fusible mass which is known as slag. This slag is usually lighter and floats at the surface and the denser particle at the surface, and therefore it can be removed easily from the impurities. Next is, after you get the concentrated ore removed from the gangue material, I will convert this concentrated ore into its respective oxide. So, conversion of the concentrated ore to its oxides. This can be done by two methods. One is roasting and the other is calcination. Okay. Why oxide it has to be converted? I said because oxides can be easily reduced to get the respective pure metal from that particular ore. Therefore, you have to try to convert the ore always to its oxides in order to obtain the pure metal. So, depending on the nature of the ores, either you choose roasting or you choose calcination. In roasting method, what happens? It is heating the concentrated ore to a high temperature but less than its melting point and in the presence of excess air. Okay. So, high temperature you have to heat in a supply of excess of air. Okay. So, when you are heating it, what is happening in roasting? The water vapor or moisture that is being removed, any organic impurities is removed as oxidized and removed. Then impurities like sulfur, if you have sulfur impurity, it will react with air to give sulfur dioxide. If you have phosphorus, it will react to give phosphorus oxide. If you have arsenic, it will react to give, okay. So these impurities are removed as volatile impurities. In case of sulfide ores, what happen? Say suppose you have a sulfide ore, zinc blend. This reacts with oxygen to give zinc oxide plus sulfur dioxide. So the sulfide ores are being converted to the respective oxides, right? So metal sulfides are oxidized to form metal oxides. Then roasting makes the ores porous, and as because the porosity is increasing, heating is in a uniform manner it can be done. The next process is calcination. Calcination is the process of heating in the absence of air or in a limited supply of air to a temperature which is high but not sufficient to melt the ore. Okay, this is usually done for carbonate or hydrated oxide ores. So you see here the difference between roasting and calcination. Roasting was done at high temperature but excess of air, but calcination is done at high temperature but usually in absence of air or a limited supply of air, and that is for usually for sulfide ores, and this is for carbonate or hydrated oxide ores. So if you take zinc carbonate, which is calamine, this will be calcinated to give zinc oxide and carbon dioxide. Similarly, calcium carbonate to calcium oxide and carbon dioxide. So this is the calcination method. Next is once the oxide ores are formed, next step comes the reduction of these oxides to the respective metal. Here what happens? Here you see that metal oxides are reduced to metals by different reducing agents like carbon, hydrogen and carbon monoxide. But what will be the reaction, whether which reducing agent you have to choose, that will depend solely upon the position of the metal in the activity series. Okay, this is the reactivity series where the metals are arranged in decreasing order of their reactivity. The top position or the highest reactive is potassium and the least reactive is gold followed by platinum, right? And in the middle you have hydrogen. Okay, lead and copper is separated by hydrogen. So these metals like sodium, potassium, they are not easily reduced, or they cannot be reduced by carbon, hydrogen and carbon monoxide. Like this is the top of the activity series. Okay, metals in the middle of the activity series, they can be reduced by using carbon, hydrogen, carbon monoxide, etc. And metals that occupy the bottom of the series or lower towards the bottom of the series, that can be, their oxides can be easily converted to metals simply by heating. Okay, so depending on the position of the metal in the reactivity series, you have to choose which reducing agent you want to use. Okay, now in the activity series, there are some facts. What are the facts? Like the metal which occupies the top of the activity series can displace the metals from their salt solutions that occupy to the lower of that particular metal. Okay, and when the difference of their position is large, that means the reaction displacement reaction will be faster. For the oxides of potassium, sodium, as I said, it cannot be reduced by reducing agents like carbon, hydrogen and water. And for oxides or sulfides or carbonates of mercury, silver, they can be easily converted to their respective metals simply by heating. And metals that are lower to the copper in the activity series, they do not rust easily. So these are some facts about the metals and their positions in the reactivity series. So there are three different cases I have said. For case 1, that is the oxides of the highly active metals like sodium, potassium, calcium, magnesium, aluminium. As because they are at the top of the reactivity series, therefore they have strong affinity for oxygen and they will not be reduced by either powdered carbon, hydrogen or carbon monoxide. Then how will I be? So chemical method you will not be able to utilize in this case. For this case, what happens? They are usually obtained by electrolytic reduction of fused metallic salts like oxides and halides. So here you are using electrolytic reduction, that also of the fused salts, either in their halide form or in their carbonate or oxide form. Okay. The cathode here is usually iron and the anode here is that of graphite. Okay. So for potassium, if you want to extract potassium metal, you take electrolyte is fused potassium bromide. So if you take fused potassium bromide, this will give you what? K plus and Br minus ion. So this K plus, which is a cation, will move to the cathode. It will take one electron and form potassium metal, and bromine minus, which is an anion, it will move to the anode, will give up one electron to generate bromine. So Br plus Br will generate bromine gas in the anode. So this you are getting cathode, you are getting the metal potassium, and anode bromine gas is being liberated. So this is basically the cathode and anode reaction. Similarly, for extraction of sodium, the electrolyte is fused NaCl, where in the cathode you will generate the pure metal sodium. Calcium, it is fused calcium chloride. Why fused and not aqueous? Because these solutions, they react with water immediately, therefore you cannot take aqueous electrolytic solution. It has either be fused or in the molten state, but not in the aqueous state. Okay, aluminium also can be generated by this method from its respective oxide. Next is case 2, the oxides that occupy of the metals that occupy in the middle of the series like zinc, iron, lead and copper. Okay, for them what happens? For them, first they are generally present as sulfide or carbonate ores. So the sulfide and carbonate ores will be first converted to the respective oxides by roasting and calcination method. Say for zinc oxide, I have zinc blend. Okay, in excess of air, this is nothing but roasting. And when I take calamine zinc carbonate, this process is calcination. Okay, so I convert to the respective oxide ores. Once the oxide ores are formed, they are treated with suitable reducing agents like carbon, hydrogen and carbon monoxide depending on the metal. So these reducing agents will then react with the respective oxides to give me the respective metal. For zinc blend, it reacts with only carbon because zinc has high affinity towards oxygen, and as carbon is a powerful reducing agent than hydrogen and carbon monoxide, so zinc oxide always reacts with powdered carbon in an inert atmosphere with producer gas present. Producer gas is nothing but a combination of carbon monoxide and nitrogen. Okay, so zinc oxide reacts with powdered coke in the presence of producer gas in a retort to generate zinc metal and carbon monoxide gas. Okay, this zinc is known as, okay, so this zinc obtained is known as zinc spelter. right? Now, sometimes what happens, the other like iron, if you take iron, iron oxide will react with carbon to give iron plus carbon monoxide. Iron oxide can react with carbon monoxide to give iron and carbon dioxide. Iron oxide can react with hydrogen to give you iron oxide plus iron plus water. Okay, so iron, copper, lead, their respective oxides can react with carbon, hydrogen and carbon monoxide and be reduced to obtain the pure metal. Sometimes what happens, it is also found that, as I was speaking of the displacement reaction, that metals that occupy higher position in the reactivity series than zinc, iron, they are sometimes used for generation as reducing agents for the generation of the respective metal. Like from manganese dioxide, when I treat it with aluminium, this forms what? The manganese metal, aluminium oxide and heat. Exothermic reaction is formed. Okay. So, this is known as an exothermic reaction and you get the metal in the liquid state or molten state, because this is a exothermic reaction. Similarly, iron oxide when treated with aluminium will generate iron, Al2O3, okay, and heat. This is known as aluminothermy. Okay, so when aluminium is acting as a reducing agent and it replaces manganese and iron from its respective oxides, the treating of the respective oxides with aluminium is known as aluminothermy. Next is case 3. What happens to the oxides of metals in the bottom of the series for metals like silver, mercury and copper? These metals are not at all reactive. They are reduced to the metals by only heating. They are less reactive. So, just by heating their oxides, you can generate the respective metal. So, you see for mercury, starting with mercury sulfide, treating with oxygen, this is cinnabar, you get mercury oxide and sulfur dioxide. This mercury oxide, when you heat it to a high temperature, will generate the mercury metal and oxygen. Similarly for silver oxide. Here what happens, for the copper ore, sometimes auto reduction takes place. What happens? You see copper sulfide when react with oxygen, it will give you what? Copper oxide and sulfur dioxide. This copper oxide will again react with this copper sulfide to give you copper and sulfur dioxide. That means a auto reduction process is taking place for this reaction. Next is coming to the last step. Here you have generated the metal, but the metal still contains certain impurities and ultra purification should be done. So this will be done in the last step, that is the refining step. So refining is a process by which the crude metal is purified. Here what happens, that the metal that was obtained in the earlier stage can contain impurities like other metals, other non-metals like silicon, phosphorus, and also some unreduced oxides and sulfides. So in order to remove them, you have to choose again some methods, and this purification will depend on the nature of the metal, the nature of the impurities, and the purpose for which the metal is to be used further. So depending upon this, you choose, there are 3 methods. One is distillation, one is liquation, and the other is electro refining. Distillation is usually done where there is difference in boiling point, okay, and it is usually done for mercury and zinc ores which has low boiling point. Liquation is done usually for metals which have low melting point like lead and tin, and electrorefining for aluminium etc. you go for electrorefining. So distillation, what happens in a chamber, if you just heat it, the metals with the low boiling point, they will vaporize fast, leaving behind the impurities, right? Liquation, what happens, you have here a hot or a molten furnace. You just drop the metal here, then as because it has low melting point, what will happen, you have a sloping hearth here, the metal will melt and therefore it will be collected here at the bottom, leaving behind the impurities because they have high melting point and at that particular temperature they will not melt. So this is the process of liquefaction. Now what is electrorefining? Electrorefining utilizes a electrolytic cell and it utilizes electrical energy to drive chemical reactions. Here what happens, there are three components in the cell. One is the electrolyte and the other are the two conducting electrodes, that is cathode and anode in a conducting vessel. So you see here, this is the electrolyte, this is the anode and this is the cathode. Electrolyte is usually the solution of the metal ion and it also contains sulfuric acid to increase the conductivity. Anode usually is the impure metal that I am taking and cathode is the pure metal, right? Suppose I have copper, okay? I want to extract pure copper from the impure. Impurities can be zinc, nickel, iron, etc. along with copper. So whenever I am passing electricity to it, what happens? This copper, this will give up 2 electrons to generate Cu2 plus. Okay, this is at the anode. Okay, this Cu2 plus will go to the cathode, will take up 2 electrons to give me pure copper. So you see this is happening at the cathode reaction. Okay, so in the cathode you get what you see here, deposition of pure copper. So pure metal is being collected at the cathode and this here you have C collection impurities. This is known as anode mud. The impurities settle down at the bottom as anode mud. So this is basically the principle in electrorefining. Metals like copper, silver, gold, nickel, aluminium are usually refined in this process. Now coming to extraction of a particular metal, aluminium. How is aluminium extracted from its ore? From which ore do you get aluminium? It is none other than the hydrated ore, that is bauxite. Bauxite is the ore from where you extract aluminium. This is Al2O3.2H2O, hydrated ore of aluminium. From here you get pure metal. Okay. Now before diving into the process, everything has an introduction. Similarly, let us know what is aluminium or who is aluminium. Aluminium has the basic symbol Al. Its color is silvery white metal. Its specific gravity is 2.2. Its electronic configuration is 283 because its atomic number is 13. Position in the periodic table, period 3, group 13. Relative mass is approximately 27 and its valency is 3. Okay. It is the most abundant metal in the Earth's crust. It is reactive in nature, therefore it does not occur in the free state, and it was discovered by the scientist in 1825 by Ørsted. Next is coming to the extraction of aluminium. Hall and Heroth, the two particular scientists, have very immense contribution in this field where they have discovered this method of extraction of aluminium from bauxite. Now, what is this bauxite? It contains 60% Al2O3, the rest being sand, ferric oxide and titanium oxide. Okay, these are the impurities. So you have to remove them first, then from alumina you will get aluminium. It is concentrated by the chemical method. So first first step is crushing and grinding finely divided aluminum, or you have to do by pulverization method. Next I said what? You have to do ore dressing, that means concentration of the ore. How will this be done? I have already discussed gravity separation, magnetic flotation, but here for aluminium you choose the chemical method or the leaching method. Okay, so this leaching method is also known as the Bayer's process. Okay, from bauxite you will generate aluminum. Okay, in this process what happens in the Bayer's process? So you have what? Bauxite, crushing, milling, I get finely divided ores. This ore is then treated with concentrated caustic soda. Okay, at a very high temperature of 170 to 180 degrees centigrade in a pressurized vessel. Okay, to obtain what? A soluble mixture of sodium metaaluminate. This is what you will generate. Okay, this is soluble. This is soluble in the caustic soda solution. And what happens to the impurities? They are not soluble, so they are precipitated. Like ferric, titanium, they are not soluble, so they will be precipitated, right? So this goes into the filtrate, right? This filtrate, which contains sodium metaaluminate, this is treated, diluted with again water, okay, at 50 degrees centigrade, right? This to obtain NaOH and aluminium hydroxide and sodium hydroxide. This aluminium hydroxide is now what? Precipitated. See, this is PPT. So, when you are diluting the sodium metaaluminate with water, you are getting the precipitate of aluminium hydroxide. This aluminium hydroxide, then what you will do again? PPT, sodium hydroxide, you have the soluble impurities are going in the sodium hydroxide. This, if you filter, what you will get? The residue is the precipitate that you are obtaining. So after filtration, the precipitate will be dried, it will be washed, and this will be ignited at 1000 degrees centigrade to obtain nothing but alumina. So aluminium hydroxide heated at 1000 degrees centigrade to generate alumina and water. Okay, so this is how you obtain alumina. So the total process or the 3 steps. So How many reactions I am having here? 3 reactions. Okay. So this total process where bauxite is being converted to alumina is known as the Bayer's process. Okay. This is basically the concentration of the ore and generation of the oxide ore. Right. Next is, after you generate alumina, you have to reduce this alumina to its respective metal, that is aluminium. How do you do? As I have already said, that aluminium occupies in the top of the activity series. So you will not be able to reduce it with reducing agents like carbon, water and hydrogen and hydrogen and carbon monoxide. So you have to go by the electrolytic reduction method. So in the electrolytic reduction method, what you have an electrolytic cell. Okay, this is a rectangular sloping tank which has a sloping bottom. Okay, the inner lining is you have a carbon gas lining which acts as the cathode. You have electrolytic solution inside the tank and you have graphite anodes dipped into this electrolytic solution. This electrolytic solution, basically the electrolytic reduction method, is the Hall-Herold's process. Here what you have, you are adding in the electrolyte. It is a combination of fluorspar, cryolite, 60%, calcium fluoride, fluorspar, 20%. So my electrolyte consists of molten alumina, cryolite and fluorspar. Okay, in the ratio of 1:3:1. Okay, and you have some powdered coke sprinkled on top of the electrolyte. The temperature is 950 degrees centigrade and the voltage is 5 to 6 volts. So now what the reactions will take place? You see, cryolite will decompose to give 3Na plus, Al3 plus and 6 fluoride ions. Fluorspar, which is calcium fluoride, will give calcium 2 plus and 2 fluorine minus, and alumina, which is Al2O3, will give 2 Al3 plus 3 O2 minus. Right? So now what happens? This, how many cations we are getting? Sodium, calcium and aluminium. So aluminium occupying the lowest in the electrochemical series, this will be migrated to the cathode, and anions are fluorine and O2 minus. So this occupying lowest in the series, O2 minus will be migrated to the anode, right? So the cathode reaction will be aluminium ion taking up 12 electron to generate pure aluminium, and anode reaction will be oxygen or O2 minus will go to the anode to generate oxygen gas. Now anode, what I have, graphite, which is nothing but carbon. This will react with oxygen to generate carbon monoxide, which will further react to generate carbon dioxide. So time to time you have to replenish the anode because you are generating, it is being depleted after reaction with the oxygen, right? So this is the total reaction scheme of how you generate pure crude aluminium, which is 99.8% pure from Al2O3. Okay? Now after this, the last step is electro refining, that is 99.8% aluminium that you are generating will be further purified by electro-refining method to generate 99.9% pure aluminium metal. But electro-refining in details is not in your ICSE syllabus, so in details I will not be discussing that. So coming to the summary, that is the flow chart of the extraction of aluminium. So the ore was bauxite, that is Al2O3.2H2O, right? First step was what? Crushing, grinding. Then comes the concentration of the ore by the Bayer's process, where I have sodium metaaluminate plus water. Reaction 1. Sodium metaaluminate plus dilution with water at 50 degrees centigrade to generate sodium hydroxide plus aluminium hydroxide as precipitate. Aluminium hydroxide heated at 1000 degrees centigrade to generate alumina and water, right? So this is the three reactions of concentration of the ore. Next is electrolytic reduction, right? Here what happens at the cathode? Pure. This is 99.8% pure. And in the anode reaction, what happens? Okay. Next, the last step is electro refining, where at the cathode what happens? What will happen? First, from the Al3 plus will take up 3 electrons to give pure Al, and at the anode you have Al minus 3 electrons to give Al3 plus. So this is the pure metal that you are generating from bauxite. So this is the total flow chart of how you extract aluminium from bauxite, right? So that's all for today's class. Thank you. Subscribe to our channel. Thank you.